All right, so you got your homework back, and I looked at question 3.5, which was going into some proofs, and in particular I looked at your direct and indirect solutions for 4C. So 4C was the following theorem: A or B, C and D. A implies not C, and therefore B. I wanted to prove that both directly and indirectly. And there's a variety of ways to do this, and I saw some different solutions. And the approach you take is not super critical, right? There's not like one approach is correct and the other is wrong. What's really important is that each step follows logically from the prior steps, and the way that you present the proof. Okay, so the way you actually write this up is a big part of the exercise. So let me show you a direct proof, but there's other versions that are available. I'm going to keep my handy cheat sheet of rules available here. So before you can use any of these things that you're given, you have to state them as part of your proof. So I might start off by just writing down all of my premises, and you want to list a reason for each thing you write. Why do I know that A or B is true? It's a premise, or a hypothesis, or a given. And similarly, I know C and D is true. That's a premise. And I know A implies not C is true. That's a premise. So most people decided that somehow the trick is to use C and D to prove that C is true, and then put that together with this to show that A is false, and then put that together with this to say, since A is false, but this disjunction must be true, that B must be true. And so that's the sort of inspiration. So how can we write this up? Well, let's start off by getting C. I'm going to state that C is true. And what is the reason for that? So if I know that P and Q is true, then I also know that P is true. And similarly, if I know that P and Q is true, then I also know that Q is true. So conjunctive simplification lets me take two things that are ANDed and then say just one of those things alone is true. So the reason for this is conjunctive simplification applied to statement 2. Conjunctive simplification is a thing, 2 is true, so the result of that will also be true. So that gives us C. So at this point, we can go directly with indirect reasoning. We can go immediately with indirect reasoning. A implies not C. C is true, therefore A must be false. But let's do this a variety of ways. Let's be a little more explicit about it. We know that A implies not C. We know the contrapositive of that statement is also true, so that's actually saying the negation of not C implies the negation of A. That's contrapositive. Applied to statement 3. And we know the negation of C is equal to C. That's something called the involution law, or double negation, if you like. And so this is telling us that C implies not A. Let me just say double negation. So it's also called involution. And now we can start bundling things together. We know that C is true. We know that C implies not A. Those two will give us not A. That's direct reasoning. Statements 4 and 6. And now there's another rule we can use, which is disjunctive simplification. Given P or Q and not P, we can conclude Q. Given P or Q and not Q, we can conclude P. In other words, if the or of two things is true and one of those things is false, the other thing has got to be true. So that's disjunctive simplification. Well, we've got A or B and we've got not A. That means B has to be true. And that's disjunctive simplification applied to statements 1 and 7, and that's exactly what we were asked to show, which is B. So that's the end of the direct proof. So important points here: list anything that you're planning to use. If I'm going to write down the contrapositive of statement 3, I've got to have statement 3 written down. Don't just know that it was given because it was stated in the left side of the double arrow and just write down the contrapositive. Make sure that you've stated the thing that you're given and then use the contrapositive to state something new. And try not to skip steps. Okay? If you skip this double negation step and go directly from A implies not C, C to not A, I'll let you have that. Okay? Because that's pretty straightforward. But anything more complex, make sure you put down all the steps. Especially these things like conjunctive simplification tells us that C is true, and then we could say that goes together with A implies not C. But don't just do that in one step. Don't just go directly from A implies not C to not A, right? Because in your head you know that C is true, and so that's going to say not A, right? List the steps. Because you can look at this and you may convince yourself that this is a true theorem. Right? The purpose of a proof is to convince the reader why it's a true theorem. Right? So you don't want the reader to have to do any thinking when they're following this. You don't want them to need any insight. They should be able to say, okay, what is conjunctive simplification? Okay, what happens when I apply it to 2? Oh yeah, I get C. Right? So they can confirm your proof is valid without having to figure out the proof themselves. Right, so I use the mental model of like a court of law where you're talking to a jury, you're trying to convince them that B is true, right? And this is a jury that can follow these rules of logic and apply them, but doesn't actually have any insight in how to come up with the proof themselves. So you're just presenting evidence. All right, so an indirect proof of this might be the following. And A implies not C. Okay, indirect proof. I like to start very first statement, negation of what we're trying to use. That's our assumption. Because everything else we write is either going to be given as true or it's going to follow from things we've already written. So everything from here on down we know is true. And when we reach a contradiction, we're going to be able to go to the very first statement, which was our assumption, and say this must have been incorrect. Right? As opposed to burying our assumption 3 or 4 lines down, and then you have to kind of hunt and figure out where the error was. So let's start off by assuming not B. And let's put that together with A or B and use this disjunctive simplification again and say therefore A must be true. So let's write down A or B. That's a premise. And that's going to lead us to conclude A due to disjunctive simplification of 1 and 2. And we know that A implies not C. Well, let's go ahead and state that. A implies the negation of C. That's a premise. And since A is true, that implies not C. That's direct reasoning. And now we're all set because we know C and D. That's a premise. And so we know C. And that's conjunctive simplification. And at this point, you're fine saying we've got a contradiction between statement 5 and statement 7. statement 7 says C, statement 5 says not C. Those directly contradict each other. I would not say contradiction at this point, though, because you haven't stated anything that's contradictory. C and D is not a contradiction to anything that you've stated. If you stated not C and D, that would contradict it. But to see that this is a contradiction, you need to go from C and D to just C using conjunctive simplification, and then see that C contradicts statement 5, not C. Right? So again, don't skip steps. Make it totally obviously clear to whoever's reading this that you've got a direct contradiction, such as C and not C. And then since there's a contradiction, we know that not B was true, and so we can say therefore B, and that's the end of the proof. So again, in most cases, it looked like people had the right inspiration for this. It was largely about how it gets written up, or in some cases, not doing the indirect proof or not doing the problem at all. Skipping steps here and there, things like that. So if you have questions about that, go ahead and ask now, or think about it and ask questions later. Because proofs are going to be critical. They're going to show up on the midterm, and they're going to be used in a lot of the rest of the course. So you definitely want to understand proofs. Does anybody know when our midterm is?
The 30th.
Oh, good. I don't have to write it tonight then. All right, we got time. All right, so questions on that homework set. All right, questions on the current homework set.
So when it's saying define the proportions of P and Q, those are assuming as like just truth tables of P and Qs?
Statements.
Statements.
Yeah. We're really not going to use truth tables a whole lot, even though I know you like them. We want to be able to state a proposition like, you know, the sun is hot. That's a proposition.
Mm-hmm.
And it could be true or it could be false. But the important part is it's a declarative statement that has a truth value. So say P is the sun is hot and Q is today is Tuesday, and show me why the fallacy of denying the hypothesis is false. Right? Argue it, right? Pick P and Q so that if you state the fallacy of denying the hypothesis, it's clearly false. Right? I'm not asking you to prove it with a truth table or propositional logic. I'm asking you to come up with examples for P and Q so that when we say P implies Q, Q therefore P, it's very clear from your example choice that that's not a valid line of thought. That's not an actual theorem. Does that make sense? All right, have you been working on the even odd proofs? So this is due Friday in class. All right, so let's move on to something else. Let's talk about quantifiers. So a quantifier is another way to create propositions out of other propositions. This is the thing we do. We take propositions, we turn them into new propositions. So let P be some proposition. That depends on the value of a variable x. For example, P is the proposition x is bigger than 10. So we're talking about a proposition that has some kind of variable in it. Okay, and the proposition makes a declarative statement that includes that variable. So we typically write P parentheses x for such a proposition. So it's kind of like a function in a programming language. P parentheses x is saying take the value of x and plug that into the proposition P. So for example, let P of x be the proposition x is bigger than 10. So it's a family of propositions. P parentheses 1 is the proposition that 1 is bigger than 10. P parentheses 12 is the proposition that 12 is bigger than 10. And we need to know what the universe of x is. So I might say, for example, x is contained in the integers. Or it could be in the reals, or it could be in the set of odd whole numbers. So P parentheses x is in this case defining an infinite number of propositions. Right? P of 5,017,000 is the proposition that 5,017,000 is bigger than 10. Right? Each value of x gives you a proposition. And so with such a family, we're going to use these a lot next week, week after. With such a family of propositions, we can ask questions like, is there any value of x for which P of x is true? And that's sometimes an interesting question. Is there any x such that P of x is true? Well, is this thing I just wrote a proposition? Is it a declaration? No, it's a question. So let me put this in the form of another proposition. There is an x such that P of x is true. So this is a proposition. If you have a family of propositions P of x, you can make a new proposition which says there is an x such that P of x is true. At least one. Could be true for a bunch of them, could be true for all of them, but there is at least one. And it turns out we use that form of a new proposition a lot. And so we have a special symbol for it. So this is called the existential quantifier. So we can write there exists an x such that P of x. And we read this as there exists an x. And again we read the colon as such that, and this is just P of x is true. So the backwards E says there exists an x such that P of x is true. So if P of x is the proposition x is bigger than 10, is this statement true or false? There exists an x such that P of x is true. All right, definitely. If x is 11, P of x is true. That's enough to say, yes, there does exist an x such that P of x. Okay, there's also the universal quantifier. and that's written as an upside down A. And this means for all x, P of x is true.
So is there a colon between the two things?
No, because the colon means such that. So there exists an x such that this is true. This says for all x, P of x is true. So if P of x is the proposition, x is bigger than 10, is it true that for all x, P of x is true? If x can be any integer, then no, because if x is 5, P of x is false. So the first proposition is true, the second one is not. But if x was the set of integers bigger than 100, then yes, for all x, P of x would be true. So let's look at some other examples. And let's just work over the integers. So for all x, x is less than 0 or x equals the absolute value of x. Is that a true proposition? How many say true? How many say false? Lots of abstains. Yeah, that's a true proposition. Because the nature of absolute value applied to integers is that if the number is less than 0, it'll be negative x. If the number is not less than 0, absolute value doesn't change the value. If it's 0, the absolute value is 0. If it's positive, the absolute value is just the number. So yes, for all x, either x is negative or it's equal to its absolute value. For all x, x squared is bigger than or equal to 0. That's true, right? Because squares are always non-negative. There exists an x such that x is not equal to absolute x. And negative 1. Absolute value is 1. There exists an x such that x squared is less than x. What's the value of x that makes that true?
Anything less than 1, yeah. Or in between 1 and 0.
Right, so if we're over the integers, there is no such x. If we're over the reals, something like 0.5 works. Because 0.5 squared is 0.25, and that's smaller. So it depends on the domain here. Depends on what the universe is. So sometimes, to make this clear, we can say something like, for all x contained in the natural numbers, P of x. And if we take the naturals to mean 0, 1, 2, and so on, so non-negative integers, what this actually means is, this is logically equivalent to saying that if x is 0, P of x is true. If x is 1, P of x is true. If x is 2, P of x is true. All of these have to be true together. We're saying for all x, P of x means P of 1 and P of 0 and P of 2 and P of 17 million and so on. So we have sort of an infinitely long proposition on the right that we know is true if the left side is true. They're exactly the same thing. Now, what if I say there exists an x in the natural numbers such that P of X. What is that logically equivalent to?
The or of all of them.
It's the or of all of those. It's saying that P of X is true for some X. So either P of 0 is true, or P of 1, or P of 2, or P of 3, or P of 17 million. But one of those has to be true. There could be more than one, but at least one has to be true. So this is really an infinite or. All right, still with me? So suppose we have two propositional families, P of X and Q of X, and we claim for all X, P of X and Q of X is true. So pick any X, we claim that the conjunction of P of X with Q of X is true. That's going to turn out to be the same as this thing on the right. Well, that takes a little brain wiggling to see. The thing on the left says if I pick any X, so pick some X in your brain, X, that the logical AND of P of X and Q of X will be true. Well, that means P of X will be true and Q of X will be true, which means for that X that I picked, P of X is true and Q of X is true, and that worked for any X. So for any X that I pick, P of X will be true. So this statement is true on the left, and for any X I pick, Q of X has to be true, so this statement is true on the right. So the AND of those two true propositions is true. And if there is some X for which this expression fails to be true, that means for that X, perhaps P of X is false, or Q of X is false. So we can say without loss of generality, let's suppose we found some X where P of X is false. Well, then this statement will be false because there's some X where P of X is false. And since this proposition is false, then false ANDed with anything will be false. So these two sides will be true together and false together, so they're logically equivalent. I'm throwing in extra parentheses. Are these two logically equivalent to each other? Left side is for all X, P of X or Q of X. The right side is for all X, P of X, for all X, Q of X, the disjunction of those. It is either yes or no. So as a class, we got it right. If no, can you come up with a counterexample? So let's let P be the proposition X is odd, and let Q of X be the proposition X is even. So the left side says for all X, X is odd or X is even. We're working over the integers still. So is that a true proposition? That's true. Any integer is either even or odd. So that's true. Okay, this proposition here on the right, for all X, P of X says for all X, X is odd. Is that true? Is every integer odd?
No.
That's false. And this proposition over here says for all X, X is even. Is that true? No. So that's false. And false ORed with false, that's false. So there's this pair of propositions where the left side's true, the right side is false. They can't be logically equivalent.
I thought of another example, an idealized P of X is a Republican,
Mm-hmm.
Q of X is a Democrat.
Right, right.
I guess
So
any two propositions that are kind of
if they're complementary to each other.
complementary.
Yeah, yeah. Well, you could say P of X is you're a Republican, Q of X is you're not a Republican, and then they'd be complementary.
I said idealized.
Yeah, yeah. All right, so change the ands to ors. It's no longer an identity. And these are just sort of getting some practice playing around with these quantifiers, and also sort of breaking the tendency we have to try to find patterns in things. And a lot of seeming patterns break down when we start dealing with quantifiers. What's the other one we need? X or. So there exists an X such that P of X and Q of X. So on the left side there exists an X such that P and Q. On the right side, we have two existential statements. There exists an X such that P, and there exists an X such that Q. Are these logically equivalent? No. Got an example?
You could just say P of X is equal to, or the proposition X is equal to 2, and then Q of X is the proposition that X is equal to 3. So then both have at least one X value where they're true, but they're not at the same time, or with the same X value.
All right, so P of X is the proposition X is equal to 2. Q of X is the proposition X equals to 3. Does there exist an X such that P of X is true? Yes, 2. Does there exist an X such that Q of X is true? Yes, 3. So this right side is true. Does there exist an X such that X equals 2 and X equals 3? No, so that's false. Perfect counterexample. All right, what about if we do the disjunction here? Exists an X such that P or Q is true. On the right side, there exists an X such that P is true, or there exists an X such that Q is true. All right, so those seem to be the same thing. All right, we can also nest these quantifiers. So let's keep working over the integers. And this statement says for all x there exists a y such that x plus y equals 0. Okay, well, one way to think about this is this is a proposition, right? This is also a proposition. And we can say for all x any proposition that we want. So this is also a proposition. So this may help or hurt. If it hurts, ignore it. Let P of xy be the prop. X plus y equals 0. Let Q of x be the proposition. There exists a y such that P of xy. So this part right in here, there exists a y such that x plus y equals 0, that's a proposition that depends on x, right? If I said x equal to 0, I can say is this proposition true. If I said x equal to 2, I can say is this proposition true. The y is kind of like a wild card or a placeholder. It's saying there exists a y such that this is true. So we need a particular value of x, right? But we don't have a particular value of y. We're saying, you know, whatever the value of x is there a y which makes this expression equal to 0? So we can think of this as a proposition that depends on x. And then we could let R be the proposition for all x, Q of x. And so R is a proposition that does not depend on a particular x or y. It's a statement that for all x there exists a y. So that's another way to look at the breaking into parentheses. But what does this actually mean? It means that for any x you can think of, pick an x, you should be able to find a y such that x plus y is 0. So do you think this is a true proposition or not? Definitely true, because if you pick any x, there exists a y, namely negative x, such that x plus y equals 0. So this is a true proposition. Okay, what about there exists a y such that for all x, x plus y equals 0? What is that saying if we break it down?
Says there exists one y that works for all x.
So does there exist one y that makes this work for all x? No. Because if you give me any particular y, I can set x equal to y plus 1, and now x plus y is equal to 2x plus 1, and that's not going to be equal to 0. So this turns out to be false.
So obviously the two cannot be equivalent.
So the two are definitely not equivalent, right? Yeah, so that's a good punchline to note here. Swapping the order of these things totally changes the meaning. Can totally change the meaning. All right, so getting the idea how these things work. And we can do other nestings as well. We can do something like there exists an x such that there exists a y such that x equals y. And that's clearly true. There's a lot of x's and y's for which this proposition is true. For all x, for all y, x is equal to y. Well, that's hugely false. Because for most x's and y's, x is not equal to y. But we could say for all x and for all y, x plus y equals y plus x. That's absolutely true. That's a statement of the principle of commutativity, saying that the order of an integer addition does not matter. All right, questions on that? All right, 5-minute break. We're going to switch gears. We'll leave propositional logic behind for a week or so, and we'll switch gears, start talking about some number theory. And then we'll come back and we'll combine a bit of our number theory with propositional logic, and we'll talk about the real good part of the course, which is mathematical induction. But we'll have a lot of fun with number theory first.
You said you're going to leave propositional logic behind, or you're going to leave quantifier logic behind?
For the most part, yeah.
So just double check on this. So it's saying like for the hash exists some y, but
Otherwise, you're going to be